Recording, and I've got audio. All right. Okay, well, start off with, does anyone have any questions from the homework? No? Okay. Well, then let's pick up where we left off. Who can tell me the difference between precision and accuracy? Okay. Not yet. Precision is about how resolved is your measurement. How many decimal places do you measure to? Good morning. Here, pass this back to them. Make sure you get the sign in on the sheet. Precision is about how many decimal places you measure to. It's how finely you resolve the measurement. Accuracy is how close your measurement is to the actual value. The example I used Friday, to kind of rather a ridiculous example, but one that I think makes the point, is we could measure the length of this room from that wall to that door, and we could measure it out to 24.7859 inches. Now that's an incredibly precise measurement, but it's also incredibly wrong. It's not even close to accurate because this room is a lot more than 2 feet wide. We also talked about estimation and, well, we didn't really talk about estimation yet. We're going to. We'll get there, I think, in 1.7. But we talked about estimating error or uncertainty. The book tells you that you should assume that the last digit in the measurement can change up or down by 1. I'm telling you that in reality it would be the next digit that could change it by up or down by 5. Okay? But let me ask you this. We're talking about estimating the error or the uncertainty, right? So who's wrong? Me or the book? Okay, and just for future reference, not for nothing, but if I ever ask you that, the book is wrong. Okay, just so you know. But seriously, who's wrong? Good job, good job. Now there's someone who learns. No, think it through. How can an estimation be wrong? Sign in sheet. How can you be wrong if you're just estimating? If I estimate that the error is 2%, and you estimate that the book estimates that the error is actually 4%. They're both estimates. So if you're close, you're not wrong. So I'm just throwing that out because I know most of you will be worried about, oh no, is this going to count against me on my grade? Am I going to lose points if I don't get this right? Well, it's an estimate. Okay, so another place where the book and I diverge, where we disagree, the book uses the phrase scientific notation and powers of 10 notation as though they are the same thing. I explained to you on Friday, they are, you could say that they're two different forms of the same thing, but they are not exactly the same. Can someone tell me the difference? You're exactly right, but the other way around. It's scientific notation that you want to have the exponent as a multiple of 3, because that will make it line up nicely with all those tables of convenient prefixes. Okay, now the book tells you that they're both the same thing. So, I want you to understand that they are not. But I also don't want you to go home and worry about, well, am I going to mark you wrong because you wrote something that the book said was right and I said it was wrong. Okay? This isn't something that's, if it does show up on an exam or a test, it'll be asked explicitly the way I asked. What's the difference? Okay? But other than that, don't feel like you're going to have to, I'm not setting you up. I'm not trying to trap you to get something wrong or to cost you points. I just want you to understand how this actually works. Why does it matter? Why do we care about the difference between accuracy? Well, we should care about the difference between accuracy and precision. You can make a measurement, you can make an instrument that's incredibly precise, but if it's not accurate, it's worthless. And this is physics. We are learning a science. This is all about what we can measure. So we do need to understand what it is we know and what we don't know. We need to understand when we make a measurement, how close are we to the actual value? Okay. That's sort of the point of what we do. But there's a whole nother reason that I want all of you to get used to thinking in terms of making estimations and approximations. And this is going to come up repeatedly over the course of the semester. And for any of you who come back for Physics 2, it'll continue to come up in that semester as well. You work in a problem. You do the math. You punch all the numbers into your calculator. You get your answer and you write it down. Does it make sense? You start doing the calculations to try and figure out, okay, how many gallons of water will this bucket hold? Well, and we're fixing today, we're going to start looking at how to do dimension analysis, unit analysis, and how to do conversions and things. All it takes is one little slip of the decimal place. And all of a sudden, you're coming up with a solution that bucket that shouldn't hold more than 2 gallons, suddenly it's got 20 gallons in it. You need to be able to look at your answer and ask, is this a reasonable answer? And if you can develop an intuition, a skill of being able to estimate what you expect the answer to be, then when you do make a mistake with your calculator and you miss hitting the decimal point and you suddenly find that 2-gallon bucket, your calculator's telling you that 2-gallon bucket's going to hold 200 gallons, it'll catch your attention. And believe me when I tell you, if you don't think about it, if you don't make it a point of asking yourself that question every time you solve a problem, those mistakes will happen, and they will be just as ridiculous as that. And you'll just they'll just slide right past you and you won't notice. Okay? It's also why I told you I want to see the work you do to come up with those answers. Because if it is, if you tell me that a 2-gallon bucket holds 200 gallons and I can look back and see where it was just an arithmetic error, you missed a decimal point, I'm not going to count off as near as many points as if you just write down that it holds 200 gallons and then it's like, well, I'm sorry, that's just wrong. Okay? I want you to learn to do the math. The arithmetic is kind of just, you got to do it to do the math. But that's not the point of why we're here. So, honestly, I don't know, whatever job you go into, you're going to have to be able to go into a situation with some kind of idea of what, you're going to be solving for solutions to problems. You're going to have some idea of what kind of answer you're expecting. And that's what this is all about. Now, we talked about units. Who can tell me the name of the system of units that we use? What system of units do we use? Say again? Well, that's the other one. No, SAE is the American. Which one do we use in physics? SI. Can someone tell me what SI stands for? It's in French. It is French, but if you just say it snooty, it sounds right. Anytime, as a matter of fact, this is a rule. You can check it out if you want to. Anytime you see a word in English that ends with T-I-O-N, it's the same word in French, just snootier. That's it. Change the accent and you've changed the language. So, what does SI stand for? It is. Only in French, it's Système International. See how that works? The French do everything backwards. You go, in English, you throw some hay over the fence to the horse. In French, you throw the horse over the fence some hay. So, international system of units. In particular, we use whereas next door in chemistry or across the hall in biology, they use, now, who can tell me what these stand for? Centimeters, grams, and seconds, and CGS, that's right. What about MKS? Meters, kilograms, and seconds. These are what are called the fundamental units. There are some other fundamental units that we'll pick up along the way, like coulombs. Of course, I'm not sure they still consider coulombs the fundamental unit, but again, they didn't ask me. By and large, especially with regard to mechanics, the laws of motion and such as that, these are the three fundamental units. Does anyone want to take a guess at what that means? That they're fundamental units. That's a good answer. What it means is that all other units derive from these. For example, if we're talking about how fast the velocity of an object in motion, how fast does the velocity change? That is acceleration. And that will be equal to meters per second squared. I did go over this notation with you, right? The exponential notation for something raised to a negative exponent? No? Okay. This means the same thing as meters per second squared. Okay, by definition, x to the power of n equals x times x times x times x sub n. Okay? This is not out of your book. This is just something extra you're going to need to know. X to the minus n is, by definition, equals 1 over x to the power of n. Okay? So if you have x to the n times x to the minus n, that means you have x to the power of n divided by x to the power of n, which equals 1. This is reciprocal. This is called reciprocal notation. You're also going to find out that x to a fraction, x to the 1 over n, change that from a 2 to an n, x to the 1 over n, by definition, is the nth root of x. So, x to the 1/2 is the square root of x. X to the 1/3 is the cube root of x. Okay? Yeah, unless some of you have interest in knowing this, if you do, come to me. I can show you why all of this is true. But unless you really want to know, as long as you know that it's true, you're good. This kind of thing does come into play, though, when we start talking about scientific notation or power of 10 notation. What if you wanted to multiply 2 times 10 to the power of 13 by 4 times 10 to the power of 8? Now, what would that turn out to be? Now, you could break out your calculator and type it in, it'll give you the answer pretty quick. But if you just multiply your factors, your numbers, 2 times 4 is 8. And then just add the exponents. Times 10 to the power of 13 plus 8, which is what, 21? So, what if you were dividing? What if you wanted to divide 4 times 10 to the power of 8 divided by 2 times 10 to the power of 13? Divide the coefficients, so at 4 divided by 2 is just 2, and then you subtract the exponent of the denominator from the exponent of the numerator. Which would be, in this case, a negative number, which means it's smaller than 1. Of course, the big benefit of using power of 10 notation is if you put something in power of 10 notation, it becomes immediately obvious how many significant digits you have. These kind of mathematical tricks for doing the calculations, they're handy as well. But frankly, scientific calculators nowadays make it so easy to multiply and divide and do the arithmetic in scientific notation that frankly, I'm not sure it isn't easier just to use the calculator. It's not like you have to keep track of a lot of stuff to do. All right. Does anybody have any questions yet? Any questions, comments, thoughts? No? Everybody still keeping up? Okay. Well, then let's talk about these fundamental units. Acceleration is measured in meters per second squared, but what is force? Force equals mass times acceleration. Mass is units of what? Kilograms. Times acceleration is meters per second squared. Well, that we give a special name to, called the Newton. Newtons are units of force. So a Newton, by definition, is a kilogram meter per second squared. Or you could write it as kilogram meter per second squared. Either way you write it, means the same thing. So, what is the fundamental unit of length? Well, of mass, we know it's a kilogram. What's the fundamental unit of length? Meters. And how long is 1 meter? 100 centimeters. And that is, believe it or not, that is not a trivial answer. That is, in fact, going to be a very significant answer here in just a few more minutes. But for right now, let's talk about the definition of 1 meter. The reason for having standard units worldwide is so that everyone, everywhere in the world will know when we talk about 1 meter, they know exactly how long that is. Originally, 1 meter was defined, and this is a significant word, and it ties directly to what I was saying, your answer is not trivial. We're going to get there. I want you to pay attention to this. I'm using this word defined. It means something. It's significant. Meter originally was defined as 1/10,000,000th of the arc length, the distance from the equator to the North Pole along the prime meridian. Okay? So, measure that length, get you a piece of rope, tack one end to the equator, run the other end all the way up the prime meridian to the North Pole, cut it off, and then cut it into 10 million equal lengths, and each one of them will be exactly 1 meter long, or it would have been back then. Obviously, that's not a very practical way of defining the length. In time, it was defined differently. Back here in the book on page 9, it tells how they changed it in 1960 to 1 meter was defined as 1,650,763.73 wavelengths of a particular orange light that came off of a, what was it, Krypton 86? Krypton 86. Now that's a pretty precise definition, and it's one that people all over the world can reproduce. Since then, they've changed the definition again, and now they've changed it in terms of the speed of light in a vacuum, which was measured with very, very high precision. At the time they changed the definition, the precision of the speed of light was known to within plus or minus 1 meter per second. And so they defined a meter as 1/299,792,458th of a second. the distance light travels in that long of a time period. Point is now, anyone that can measure the speed of light with precision can also reproduce a meter with precision. You're going to find that, find it out right now. How many of you are asking this fundamental question? You certainly should be. How could you possibly measure that length of time with that level of precision? And the fact is that we have come up with ways of making measurements with incredibly high degrees of precision. Can we ever measure that length exactly? We can never measure anything exactly, because every time we measure anything, there is always going to be some finite precision involved. There's always going to be some uncertainty in the measurement. But because we can quantify that uncertainty, we can now make measurements within an arbitrary precision. In other words, we can say up front, we need to know this length to within this much variation, to within this much uncertainty. And once we've defined how much uncertainty we can tolerate, we can live with, then we can measure that length to that precision. Now, that is true always of every measurement. When is it not true? Every time we measure anything, there will always be some level of uncertainty. When will that not be true? When will there be a zero uncertainty? When will there be absolute perfect precision, plus or minus zero? And this goes back to your answer of all of it. It happens when we define something. Okay? We may not be able to measure a meter to an absolute plus or minus zero precision. But once we have a meter, we know that it has exactly 100 centimeters in it, plus or minus zero. Okay? Because that is a definition. The meter is defined as being 100 centimeters long. So whatever our meter is, 1 centimeter is 1/100th of that with absolute defined, definitive precision. How many inches are there in a meter? Something like that. But the conversion, and we're going to start talking about conversions here pretty now, is 2.54 centimeters in every inch. Now, if you make a measurement of something as so many miles long, then you have an uncertainty in that measurement. But once you have that, you know that you have so many miles, you know that every mile, by definition, is 5,280 feet. You can then convert that mile into 5,280 feet per mile, and then you can convert those feet into 12 inches per foot. There is absolute precision when you convert inches into feet, because 1 foot, by definition, is 12 inches exactly. No error. When you then convert those inches into centimeters, you convert those inches into 2.54 centimeters for every inch exactly. That's that is a definition. And once you have the centimeters, then you multiply that by 100 centimeters in every meter. And that, again, is a definition. There are exactly 100 centimeters in every meter. So, when you are doing the arithmetic, when you're doing the math, if you have a measured value, then that will limit the number of significant digits you're working with. But if you're working with, say, somebody measured something out to 4,387 feet, and you're converting it into meters. When you do the conversion from inches into centimeters, you don't have to take into account significant digits there, because that is, by definition, precise, exact. You only consider the significant digits of the measured values. So, what's the answer to the question? Every time you have a measured value, you have some uncertainty. When do you have no uncertainty? When is your precision absolute, perfect? When you are dealing with a definition. When a quantity is a defined quantity, there's no uncertainty. Okay, time. Standard unit of time is second. And the second is defined, well, originally it was defined as 1/86,400th of a mean solar day. The time it takes the sun to go from sunrise to sunrise. Why do we say the mean solar day? Thank you. A day is, from sunrise to sunset is not the same amount of time every day. It's different every day because the Earth is precessing on its axis. Let's see. Yeah, now they have defined it as the time required for, and I'm still on page 9 if any of you are interested in following along. The time required for 9,192,631,770 oscillations of the radiation, the light, emitted by a cesium atom when it passes between, when the electron gives off a photon between two particular quantum states. Basically it's the same as they used to define, the way they used to define length based on the wavelengths and how many wavelengths of this particular color of light that came off of krypton. Well, they do the same thing for the second, but they use a cesium atom and a whole lot more oscillations. Give you a couple of tables here at the bottom of page 9. You're going to find, especially when you start working with scientific notation or power of 10 notation, you're going to find that you deal with some very, very, very tiny numbers and some very, very, very huge numbers. And they're not always going to be intuitively meaningful to you. Okay? Look at this table here on some typical lengths. They talk about the diameter, approximate diameter of a proton. They put it at 10 to the minus 15 meters. That means you write down 10 and then you move the decimal place left 15 times. The diameter of an atom is approximately 1 times 10 to the minus 10. So it's, again, how meaningful is that to anyone? It's not. There is nothing in your experience from your perspective that will make that intuitively meaningful to you. Which is why it's important to learn how to deal with these numbers, to make measurements, to understand the precision, because that's really the only way you're going to understand these kinds of numbers. You can talk about how many light years it is between here and another galaxy, but how meaningful is that to anyone? What does that mean? It would take you, 15 million years traveling at the speed of light to get from here to that galaxy. What does that mean? It can't make it just. It can be meaningful to you to say, how far is it from Tulsa to Oklahoma City? Oh, it's about 90 minutes or less, depending on who's driving. Okay. Well, that's actually kind of nonsensical if you think about it, because you just measured a length, a distance in terms of time. But it's not meaningless because it's an intuitively obvious reference for all of us. We all know what it's, how fast you go when you're traveling on the interstate and how long it takes you to get from point A to point B. So it's not unreasonable or uncommon for people to talk about distances that they travel in terms of the time it takes. It would not be meaningful for us to talk about things, distances, especially these tiny distances, in terms of the time it would take light to cover that distance. That would just be meaningless. It would just be more big numbers or little numbers or big exponents. Kilogram. We talked about the standard unit of mass is 1 kilogram. Who knows the definition of the kilogram? By definition, it is 1,000 grams. But what is the standard definition that defines the quantity of 1 kilogram? This one is boring. There is a particular bar of platinum iridium that they keep somewhere at the World Standard Bureau of Weights and Measures, or whatever they call the place. This particular bar of iridium, by definition, is 1 kilogram. So, that bar we know is exactly 1 kilogram plus or minus 0. That's all we know. Everything else is a measured mass. Everything else we talk about how much mass it weighs, it's measured. Now, we can convert it, we can weigh it in grams and convert it to kilograms. And the conversion will be absolute, because that involves a definition. But ultimately, it all ties back to this 1 bar of iridium. They make duplicates of it that they pass around to labs around the world that specialize in calibrated metrology and such. Yeah. We talked about the difference between power of 10 notation and scientific notation, and the difference mainly involving those prefixes. 1 kilometer not just what by definition 1 kilometer equals 1,000 meters, because kilo is defined as 1,000, or 10 to the 3. You have a hard drive on your computer at home that's measured in megabytes. What is mega? Somebody? Surely y'all know this one, right? Millions. Notice how we added 3 zeros. What's the next one? Or if you're Doc Brown, giga. Giga. Thank you. $1 billion. Or 10 to the 9. What if we go the other way? We started at 1. What if we go to 10 to the minus 3? 1/1000th. What's the prefix? Say again? Centi would be 1/100th. Deci would be 1/10th. Say again? Milli. Now, actually, there's deci and then centi. Deci would be 1/10, or 10 to the minus 1. Centi would be times 10 to the minus 2. That one we use because of CGS. Centimeters are convenient and handy for us to use. Once you get, also going up here from 1 to kilo, you would also pass through deca would be 10 meters. And I don't really know what the 100 meters would be. I'd have to look it up on the table. Milli is hecto. Thank you. And that would probably relate to the hectaker, which is another obscure unit of measure. What would come next at 0.001? What do we went to 0.000001? Or 10 to the minus 6. Micro, or 1 millionth. There is a symbol. We use the Greek letter mu, lowercase Greek mu, to signify micro. It looks like that. Actually, that looks too much like an actual M. Let me see if I can do this better. Looks like a lowercase u with a couple of extra tails. That's a micro. And a micrometer would be 1 millionth of a meter. This one you might want to make note of. There's a special name for that one. It's called a micron. So when you hear people talking about something measured down to the micron level, that's what they're talking about, 1 millionth of a meter. Any of y'all involved in engineering? You know what a mill is? One-thousandth of an inch is a mill. Okay. Don't confuse a mill with a milli. But they both relate to the word, to the idea of a factor of 1,000. See, micron, micro. What would 1 times 10 to the minus 9? 1 billionth. Nano. A nanometer, 1/1 billionth of a meter. A nanosecond, 1/1 billionth of a second. Computers and high-speed digital electronics today are measured in nanoseconds. Just to try and give you a bit of an intuition about bridging this gap between these incredibly tiny numbers and incredibly large numbers. How many of you, show of hands, how many people in this room are less than 30 years old? And I'll put my hand down now. Every one of you. That means that not a single one of you has yet been alive for 1 billion seconds. There are literally more nanoseconds in 1 second than there are seconds in 30 years. Okay? So, just a little tidbit of factoid to kind of put some of this into a little bit of perspective for you. We talked about fundamental quantities. The book calls them base quantities, and and how other units are derived from them. The coulomb is a fundamental unit of electric charge, and if you have 1 coulomb of electric charge passing a point in a wire, every second you have 1 amp of current flowing. So an amp is a derived unit of coulombs per second. Okay, now that I've told you that, I'm going to give you a heads up warning if any of you are in the electrical or electronics program. In the last few years, they've turned that completely over and they've said, no, the coulomb is now the derived quantity and the amp is the fundamental unit. So I don't know why they did that. I don't really care. It still makes the point that you have fundamental units and then you have derived units. Meters per second, meters per second squared. Meters is distance. Meters per second is speed. Give it direction and it becomes velocity, but we'll get to that in a week or two. Meters per second is speed. What's meters per second squared? Acceleration. Meters is distance or position. Speed is change in position per unit time. How fast does your position change? Acceleration is how fast does your speed change or your velocity. Kilograms per meter. Kilograms meters per second squared. That's a unit of force. We give that one the name Newton. We also have, if you have so many newtons, force times distance. So you have meters, kilograms, meters squared per second squared. You have joules. If you have so many joules per second, or kilograms meters squared per second cubed, you have watts. Okay. Point is, and don't worry about trying to remember these other units, but as we get to different units that you need to know, I'll point them out to you. What I want to get across to you here is that these units are derived units from these fundamental, or as the book calls them, base units. Now, we've talked about this converting units, because when we start converting units, we're using definitions. And I want you to see, because this will also involve this exponential notation that we were just using, that I explained a little bit about to you. What if we have a measurement of 5,000 let's say 5,000 feet. How many meters would 5,000 or in 5,000 feet? Okay. Well, we know that there are 12 inches in every foot. So we multiply 12 inches per foot. Okay. And I'm going to write it. No, I'm just going to leave it like that. 12 inches per foot. What happens to the feet? Feet divided by feet becomes unity. Unitless 1. So we got 5,000 times 12, or what's that, 60,000 inches? Yeah. Don't trust me to do the arithmetic in my head, ever. Okay? Just giving y'all a heads up. However, whatever the product is, that's how many inches we have, because inches are the only units we have left. But we also know that for every inch, we get 2.54 centimeters per inch. Well, now the inches cancel out. And we've got a number that is in terms of centimeters. We know that we get 1 meter for every 100 centimeters. Right? Now the centimeters have canceled out. And we've got a number in terms of meters. Someone with a calculator, 5,000 times 12 times 2.54 divided by 100 equals? Say again? 1,524 meters. If this were a measurement, what would our answer be? Nope. Nope. Now here, this is times however many zeros of significant digits you need. Same here. This is 100.0000 as ad infinitum. Same here. This is 12.000 ad infinitum. Infinite significant digits in every one of these conversion factors. How many significant digits do we have here? Just 1. Because this would be written 5 times 10 to the 3. So what would our answer here be? It could either be 1,000 or more accurately, this would round to 2,000. So our 5,000 feet, measured at 5,000 feet, would be 2,000 meters. What if it was measured at 5,012 feet? Well, again, do the multiplication and come up with a 4-digit number over here. But now we've got 4 significant digits. So we would have 4 significant digits in our result. And it would be something much closer to that 1,524. That is how you use significant digits. We will talk about more converting units more on Wednesday. Any questions? Anybody have any homework to turn in? Everybody sign the sign-in sheet. Make sure you sign it before you go. You did. That depends. Is your name Logan O'Connor? Then yes, you did.